So I'd like to explain how a session works when running the Octave code spike sorter. Here's a listing of the code. It's about 1,600 lines long. It's written in Octave. But this code, it actually runs also in MATLAB. So if you want to use MATLAB, you can use MATLAB to run the code. We're not going to actually change the code. We're just going to run it. So you can click this icon here to run the code. Or you can type the name of the code here in the command line. So I'll just click this icon here. And now we're going to enter the recording name of the file that was generated when we recorded the extracellular signal. So the name of our file is called experiment.wave. Next, the code asks us whether we want to use a manual selection for the spike selection criteria. So we can choose any two of these or when we use the manual selection, or we can just use the principal component analysis, which is another algorithm to basically distinguish one spike from another. So let's say we want to use the principal component analysis algorithm. The next thing it asks us is whether we want to plot the entire signal or we want to just plot the selected signal. So we're going to plot the entire signal here just to see the entire recording. This is good to do the first time around. So here in figure 3a, we see the entire recording that was generated from mechanical stimulation of a hissing cockroach leg. The stimulation occurred here, and then we have other points here where a mechanical stimulation occurred. Here's another point where a mechanical stimulation occurred. So we need to determine where we're going to begin our analysis. Typically, when we analyze the whole signal, we would say, okay, we're going to analyze this portion of the signal. So we need to enter the start time. We're going to begin our analysis, say 45 seconds. And the end time, where we're going to end the analysis, say 100 seconds. So we're going to be analyzing this portion of the signal here. We also need to enter a minimum threshold. So we don't want to analyze every single spike here. There's a lot of noise to play in these signals. So we want to only analyze spikes that are above a certain minimum threshold. So let's say we want to have a minimum threshold of 0.145. So now we're going to extract this portion of the signal here, which is shown in figure 3b. The program then asks us whether we're happy with our selections. If we're happy, we can enter 1 for yes. If we're not, we'll enter 0, and this session will end. So we'll say we're happy, we're going to enter 1, and now we're going to find the location of the peaks for that particular selection we chose. So we're finding all the peaks that are above that minimum threshold. The algorithm actually looks whether the negative portion of the action potential is below or exceeds that that threshold here. But then we actually look at sometimes when you find the negative part that exceeds that action potential threshold is actually same part of the actual positive part. So we have to consider that. Okay, so we have now found, it states here, we have found 1,174 spikes that are above that threshold. We're also plotting here the coefficient of variation for our manual selection. And the coefficient of variation is important because it shows you if there's a lot of variation in that particular spike selection criteria. So if this number is very high and it ranks them here, that might be a good selection criteria to use if you use the manual selection. Or if it's very low, a lot of the spikes typically had that same height, so we might not use that. Okay, so we're now calculating the distance between all these scores here. The algorithm also stated that we're using the principal component analysis algorithm here. So we didn't choose to use the manual selection here. If we did use the manual selection, we would have stated the different criteria. So this takes a little bit of time because we take a spike and find the distance using these scores to all the other spikes. But we're almost done here. We also have a little note here that, we're going to start adding scores to our groups of spikes here. And if they're being added too quickly, we can reduce this parameter here. And if they're being added too slowly, we can increase it. So here we have basically our spike scores, where we're using the principal component score 1 on the horizontal axis, principal score 2 on the vertical axis. And we started coloring in some spikes that are very similar. They're very close to each other in proximity. Now, we currently have 46 scores in this spike cluster, and we can say, well, that's good enough. But we might want to add a few more. I mean, they look fairly similar here, very close to each other. So let's say we want to add a few more. And we can see we increase the number of scores. We now have 132 scores in this spike group or spike cluster. And let's do it one more time. So now we have 197 scores, and that's a good set of scores to work with. You want to work with too few scores, because then it may not be sufficient to actually do the full analysis. So then it asks us, do you want to continue? And we're going to be happy, say we're happy with these set of scores here for that cluster. So we don't want to continue adding to this current cluster. We're going to now enter 0. And now it asks us, do you want to construct a new cluster? And let's say we want to construct a new cluster. We'll enter 1. And now it's going to color in another set of scores here. And these are colored in green. And it says, well, you have 61 spikes or scores in this cluster. Is that good enough? Well, we'll say we want to add a few more. So we're going to hit 1 here. And now we have 133 scores. So that's a good representative cluster. We don't want to make it too big, because the bigger you make, the more dissimilar the spikes are. So let's say we're happy with these 2 selections. We're going to stop adding scores to this cluster. We're going to enter 0. And it asks us again, do you want to build another cluster? We could build another cluster, but we're going to stop adding clusters, so we enter 0. So now what the algorithm is going to do is they're actually going to overlay the spikes from each of these clusters. It overlays them so the peak coincides. So we can see here are the green ones, and we're plotting the average value in black, and here are the red ones. And they're fairly similar. They're not going to be perfect, perfect match, but they're fairly similar. All right, so we're going to now, if we're viewed this long enough, we're going to hit enter in the command window. And the algorithm will plot a small frame here. Here's plotting just the first 2 seconds, so you can see the actual spikes within the original recording, and they're highlighted. So the red have been highlighted and the green have been highlighted. You can increase the size of this window here, or this time frame, if you like. We've only used 2 seconds. Now what the algorithm is going to do is calculate the distance between 2 successive spikes, and that's called the inner spike interval. So we have one inner spike interval here, another one here. There's a red spike here. It's kind of hidden behind the green spike, but there's another inner spike interval here, another inner spike interval here. So a number of different inner spike intervals can be calculated using the distance between 2 spikes of the same color. And then we're going to do it for the same for the green spikes as well. Then, once we have the inner spike intervals, we can calculate the frequency of the firing frequency by taking the reciprocal of the inner spike interval. So let's continue. And what it's going to do is show us analysis using that inner spike interval. So for that selection here, and using the red spikes, we can see how the frequency changes in time. There's a lot of variation, but here I plotted an average value of the frequency and how it changed in time. And here I show how the average value of the inner spike interval changes in time. Again, there's variation around this average. We can also plot the distributions. So here are the distributions of frequency, the number of counts with this particular frequency, and we can plot the inner spike interval distribution as well. So that was for the red spikes, and we can do the same for the green spikes. We hit return, and we see the same analysis being done for the green spikes. And that concludes the algorithm. We can actually rerun it if you're not happy. We actually generate figures. The code generates figures that you can include in a paper or a poster. So you can include these figures. So I'm going to end now the session.